Welcome back to Cyber Timeless, where cybersecurity knowledge never expires. And in today's video, we're diving deep into stack-based overflow on Linux architecture 86. We'll explore how memory works, how vulnerabilities happen, and how attackers exploit them. If you're into ethical hacking, if you're into exploit development or low-level security, this one is for you. So let's get started. In this video, we are breaking down one of the most classic and powerful vulnerabilities in cybersecurity, the stack-based buffer overflow. And even though modern systems include protections like the ASLR and the DEP, buffer overflows are still extremely important to understand, especially in embedded systems, IoT devices, and software written in C or C++. This practical walkthrough focuses on Linux architecture 86 and shows how exploitation works at the memory level. Let's get into it. So this is the stack-based overflow. So we begin by SSH into the victim machine. So we're going to use the command SSH the user HTTP student at the target IP, and then we put the password and we put enter. So buffer overflow are caused by incorrect program which cannot process too large amount of data correctly by the CPU and can therefore manipulate the CPU processing. So while we wait for the IP to come up, now we have the IP. So we SSH HTTP student at the IP and we click enter and yes, and then we put the password. To make it easier for me, I'll be copying and pasting the password to make this training video faster. So that's the password and we click on enter. Now we are in the victim machine that will be accessing the binary, the program, which we're going to be debugging. So first let's check what we have in it. So we have ls, we have the bow function. Now let's try to debug the function. So that's the command. If you look up here, you see I'm going to be going through the notes as well, so you can have a quick understanding of what I'm doing. So that's the function there, gdp q for silent, then the name of the program, and here the name of the program is bow. So we've done that. Now let us check for the CPU registers. So we do that with the disable main function. There we go. So now we can see the functions. We can see the CPU registers, and that's the answer for the first question over there, which is the call bow function. So that's the answer for the so what we do is simply doing the info registers, and the info registers is going to give us our answer. So that's the first answer. Now let's go to the second question. So one thing you need to understand here is there's also a way of changing the output. We can do that with the set assembly flavor input. That is, we can actually change the way it looks, and we can do that. We can change that to the Intel syntax. And what's the difference? Many might ask. The difference is in the, you notice there we have the percentage, but in the Intel we don't have the percentage. In the Intel we just have, so it's easier to be read using the Intel syntax. It's way easier. So we can see the call function there. We can see the CPU registers. We can see all the functions that is needed in it. So that's just the only difference. That's the only difference. Every other thing remains the same. So now let's go to the second question, which is take control of EIP. So to take control of the EIP is one of the most important aspects of stack-based buffer overflow to get instruction pointer under control, so we can tell it to which address it should jump. So this is very important when we are going to be putting our payload. So what we're going to do first, we're going to check info registers and see EIP, see if we have any information on that. As we can see, we do not have any information on that. We do not have any information on the EBP as well. So let's go to the notes to get the command. So this is the command we'll be running: run python c print /55 1200. So many might be asking what that /55 is. This /55 is the buffer overflow. So if we have the correct amount of the buffer overflow, we should be able to make the program crash. Now we've made the program crash. Now, as you can see, that's evident with the 0/555555. Initially we didn't have any of that, but now we are having instructions on that. So you can see that the EPP and the EIP has actually crashed, and as well if you see the ESP has crashed. So remember that it always starts with, it also is the memory address. It always starts with the memory address as well. So now that we have been able to identify the number of buffer overflow we need in order for you to crash, we can now use another command to create that number of buffer overflow, and so that we can be able to take control and get the offset amount, get the offset number. Yeah, the offset number. So I'm going to be using another terminal to create that. So we're going to hit enter. So this is the strings, this is the incorrect, this is the string, this is the large amount of data that we can successfully put into the code, that's the command there, and that's going to give us the memory address where we can use to control the EIP. So it's very simple. What we're going to do, we're going to copy and paste it there, and while we copy and paste it there from the pattern that we created, as the 1200 pattern that we created, what we're going to do with that pattern is we're going to copy the whole pattern, and then we're going to paste the pattern in the command there. So I'm going to paste it in the command, and I'm going to click enter, and then yes, and then click enter again. Segmentation for the program has crashed, and then click enter again, and now we can see that we now have the memory address. So this is the memory address, which means that we have finally been able to take control of the EIP. Now that we've been able to take control of the EIP, the next thing we're going to do now is to try and find the offset. So let's try to find what is the exact amount, that is the exact number of buffer overflow that is needed. So that's just in case we would need to do our payload later on to be able to gain a reverse shell. So what we're going to do now, we're going to get the exact amount, which is 1036, which we have eventually gotten. Now that we know the exact amount, that's what we're going to be working on. That's what we're going to be working on to get our payload. So that is going to be the shell code. That exact amount is what we're going to be working on in order to be able to get our shell code. And if you see that if I click on enter, and that's the x85 is the buffer, then we have the NOPs and the shell code, and then the EIP, this is the 4 number is the EIP, and the way we click enter, we can see that we have been able to take control of the EIP. So yeah, we've been able to take control of the EIP, and if we go to info registers, we see that the EIP is going to change. So now we have 0666 for the EIP, and for the EBP we have 0/555 for the EIP. So that is how it's possible to take control of the EIP. That EIP is very important. There are 4 segmentation. We have the buffer, the NOPs, the shell code, and the EIP. This has to be really understood, and to get a better understanding, I'll encourage you to go on HackTheBox and try and recreate this yourself, so you can understand. You can better understand what I'm doing. So that's the answer. So the EPP answer has been given, so we'll be able to get it. So now let's determine the length for the shell code. In order to determine the length for the shell code, we should find more space. We have to perform the act to get the number of space we need for us to perform the action we want. So we'll be using a simple command, msvenom. We'll be using a simple command to generate the shell code. So it's the shell code that I'll be using in order for us to be able to to gain a reverse shell for us to do our exploitation, for us to exploit the system. So it's asking what's the number. So since in the previous example we've got 1040, normally the theoretical number is always 100 for the NOPs and the shell code is 150, and if you do an addition of 100 and 150, that's 250. So the answer would be 250 bytes. That's how large our shell code theoretically become if you count only the NOPs and the shell code, which is 250 bytes. So that's the answer for the question here. And so that's the magic number, like they said. So in order to identify the bad characters now, so to identify the bad character, what are the bad characters? These are magic numbers that determine the file type. These are objects, different platform. Gradually this computer was transferred to in order for us to understand, and these bad characters are characters that do not align with the shellcode, and these are characters that we need to remove from the shellcode in order for us to be able to successfully exploit the target, the target of the exploitation, for us to escalate the privilege. So this as you can see, that's an example of the shellcode that was just printed out now. One thing you must know is that if you're gonna be generating the shellcode, you have to generate the shellcode in a linear order. That is, if you copy and paste the shellcode in this format, you might not get it. So in order to generate the shellcode in a linear order, there's a certain command you need to put to generate it in a linear order. For those who are going to be attempting this example, when I mean a linear order, I mean like now this is a character list. It has to be in a straight format. It has to be in a straight format, just like this, right? So now I'll copy and paste that, and I'm going to paste that here. So I'm going to paste that here. So I'm going to click enter, right? So now if I click enter, it's saying no shellcode created. So let me create a shellcode. So I'm going to output that to a shellcode. I'm going to output that to a shellcode, and after I output that to a shellcode, then I'm going to you see it's going to output the shellcode. Then I'm going to hit the command that would make it to be in a linear format, just like this, so that it's going to be able to align well with our payload. Now this is the format that is in linear order, it will align well with our payload in this format. So the next thing I'm going to do now is I'm going to now attempt to use this command I'm going to attempt to use the command that's available to exploit the system. So what I'm going to do now is let us run this command on our machine that's on the debugging machine, right? So what I'm going to do now is I'm going to remove this previous command that's on it, that's it, the previous character that's on it, and put the one that we just generated. So I'm going to put this one that we just generated now. I'm going to copy that, and I'm going to put that in that slot there. So this is me copying it. I'm going to copy the character list. I'm going to let you all understand how important this is at the when we do the final the final model. So I'm going to paste that here. So I'm going to paste that here, and I'm going to click enter. So now I'm going to click yes, and then we have a warning here, ignore null byte in input. Null byte means that that is x/x 00. So now we're going to run this command and /x/200xgb esp to be able to get the bytes that we've just been able to we've just input the bytes. So I'm getting an error here, so let me look and see what I did wrong. Okay, so it's saying, so first I need to So what's happening here is, why it's showing that there's no registers there is because of the initial stage. You know, in the beginning stage, we attempted it at first and there was no register. So now it means that we have not actually taken control of the EIP yet. So we have to take control of the EIP. You know, we have to take control of the EIP. There's a command we're going to use now to take control of the EIP. So let's reattempt the, and also I think we have to put a breakpoint here. Yeah, so a breakpoint is important because if you don't put a breakpoint, it's gonna crash and it's not gonna tell us why it crashed. So let us put a breakpoint. But before we do that, let's try info registers and see. Now we do not have any information there. But if we now attempt to put a breakpoint there, now we have a breakpoint there. Now let's attempt the registers again and see what happens. It says there's still no registers there. Okay, so when you come across this kind of situation, you have to go back and see where you missed out in any of the informations. So now I've attempted that again. So I have a breakpoint. I have a breakpoint there. If I try again, I have this information. That's from this information. These are the bytes that we're going to see. So the first thing we're going to do is that we're going to look for where the buffer started from. So we'll look for where the buffer started from, which is the 0/55. That's where the buffer started from. And then we're going to look at where it ends. So we're going to go down to where it ends. We're going to go down to where it ends, and from where it ends, we're going to now start checking for any abnormalities in numbers. So if you can look, if you see, we have 0/55, that's where it's end. But if you notice, we don't have 0x00 before the 0x01. So that is the first. That's the first bad character. So that is 0x00 is the first bad character. So we'll do that we'll do that until we've removed all the bad characters. So we're going to do that until we have removed all the bad characters. So we're going to keep on going through that, removing it up until we've removed all the bad characters. When we've removed all the bad characters, that's when we can now finally when we've removed all the bad characters, that's when we can finally use the shellcode to exploit the system. So what I'm doing now is I'm looking for more bad characters. That I'm going to remove. Yeah, so you need to take time to look for bad characters. There are actually some simple commands you can use to remove bad characters. So there are actually some simple commands. If you go online and go and do a search, you see some simple. So that the bad characters I found is the x00, x09. Those are bad characters, and you can see bad characters like other bad characters like x09, x01. So you can see from this 0x08, there's no 0x09 before the 0x00 started, and after the 0x00 started, there's no 0x0A before the 0x0B. So to make it easier, this is a better way of automating it to be able to just randomly remove all the bad characters at once, which I would encourage you to do than doing it manually. So yeah, so this is me just trying to check for any more bad characters, because it's very important you understand why you need to remove all the bad characters before you move on to the next stage. Yeah, so it's very important you understand that. Yeah, so that's the most important thing. So when you remove all the bad characters, then you're going to recreate the character list again. And when you recreate the character list in the command, you're going to be putting the bad characters that was found on the command list to be able to successfully exploit the target. So that's what you're going to be doing. shellcode. So now that we've been able to identify the 4 bad characters, we can now generate our shellcode using this command. The 4 bad characters we identify is 00, 09, 0A, and 20. So we're going to be using this msf command to generate the shellcode that we've identified. So the command is simple. What we're going to do is we're going to generate the shellcode on our terminal, not on the debugging terminal. So on the terminal, we're going to generate the shellcode on our terminal. What I'm going to do is I'm going to copy and paste the command here. As you can see, now it's going to output it to a shellcode. Now if I remove the shellcode just to output it on the system, what we can see now is that it's not in a linear format, but in order to be able to exploit the target, we need our shellcode to be on a straight line, if that makes any sense. So I'm going to be using this command to now make it to be on a straight line. Now it's on a straight line. Now we go back to the debugging tool. So this is very important for us to know. Now we've been able to we're going to use this command to exploit the shellcode. So we're going to be using this command to exploit the shellcode. All we have to do is the command we just output, we're just gonna copy and paste that command and put it in between where the shellcode, that's where you see, that's where we're going to put it. We're going to put it in between there, and that's it. That's everything. We have access to, we've already gained access while our netcat is listening. We've gained access. So let me do an example here. So we're gonna remove this carefully, and then we're gonna paste what we've done there. We're gonna paste this here. If you notice, we have not put on our netcast. Our netcast is not listening yet. I'll explain that in the final module. So if I copy and paste there, you notice that we've now, if I click on enter, now, what would you notice? You would notice that we've been able to successfully successfully control the EIP. So since the breakpoint is on, we're able to control the EIP. And if I now go out of that Q and N, so now this is the exploit that we're going to be using in our final module. This is the exploit we're going to be using to gain access, we're going to be elevating our access to root, and from the root we are going to be reading a file on the root. So we're going to be using netcat reverse shell listener. We're going to be using that to elevate our access to the root, right? So that's what we're going to be doing. So yeah, so moment nc nlvp 31337. Normally the way it works is we are going to have to leave. We're going to create a new terminal. Now let's go straight into the skills assessment. So let us determine the kind of file that we have there. And to determine the file type, let's gain access to the system first with the SSH. So I'm trying to gain access to the IP because this is a different IP for the skills assessment. So I'm going to put the password there. So then that's the password. Yeah, and then now let's identify the file that we'll be using. That's the binary we're going to be using. So now to identify the file type, we're going to use the file leaf/msg will tell us that it is an ELF32-bit. That's what it's going to tell us. As you can see there, it's an ELF32-bit there, 32-bit. So that's the answer for the first question. So now the second question: how many bytes in total must be sent before the getting access to the EIP? So let's run this command: glb/q leave msg. I need to put gdb Q is for silent. And so now we've done that. So now let's now disassembly main. So now we are reading the function. Now let's go straight to the function of what we're looking for. So we'll convert that to the Intel. Let's convert that to Intel to make it easier to read. So now we've converted that to Intel, and as you can see the call function there, So now that the question is how many bytes must be sent before reaching the EIP. So if you remember, in the previous stage we ran a command in the previous stage. So to get that command, we'll be using this run python c print /55. That's the buffer. It's asking how much buffer do we need to crash the program. So in order to do that, what I'll do is in the previous section, if you notice, we used 1,200, but I'm going to increase it to 5,000. So I'm going to increase it to 5,000, and yes, the program crash. That's what we need. So now that we are able to understand that the program has crashed, now you can see that the program has crashed. If you look at the EIP and the EPP, they are the same number, and the EBX is still the same number. So we're going to be running the other command now to get the offset. So remember, if you put too little of the buffer, it's not going to crash, but we want it to crash, so we are going to put too much of the buffer. So now that we've been able to do that, now let us now create the pattern. So instead of 1,200, I'm going to edit it to 5,000 pattern, because that's the pattern we use for the program to crash. So then now that after doing that, then we'll go and use the second pattern. This is to take control of the EIP. So this command is to take control of the EIP. So we use this and put there, and then we remove the pattern, and then we copy the 5,000 pattern that we initially created and paste it there. So that's what we're going to do. We're going to do that on the debugging terminal. So in order to crash it, it has to be on the debugging terminal. So now let me copy the 5,000 patterns I've created, copy and paste, and yes, enter, and enter, and then that's we've gotten the address, memory address, that we have taken control of the EIP. So if we go to info registers, we see now that that's the memory address, that's the EIP, that's the address. So that's the memory address we're going to use now to calculate the offset. So we'll be using the memory address now to calculate the offset. Now we have that memory address. The next step would be let us calculate the offset. As you can see, we have the EIP, we have the EBP, and we can do info registers ESP. We have the ESP, and info registers EIP, and we have the EIP. So now let us calculate the offset. So we'll go back to the command that we used, the initial command that we used. We'll go back to that command to calculate the offset. And now that because we already have the memory address, that after we took control of the EIP, we got the memory address. So we're going to be putting that memory address after the /q. We're putting that memory address, and the memory address I'm talking about is the EIP. The memory address is the EIP. So we'll be putting the EIP there. The EIP here I'll copy the EIP and I'll paste it there, and it's going to give us the exact. Okay, the error came out because I'm doing that in the debugging terminal. So I shouldn't be doing that in the debugging terminal. I should be doing that in my own terminal. So I'm going to go back to my own terminal, and I'm going to do that in my own terminal, and I'll click enter, and I've gotten the offset for 22060, and that's the answer. So I'll go down to the question. Yeah, that's the answer of that is 20260. So now let us now use that 2060 now to take control of the EIP. So as you can see, if I click on enter here, it's not going to operate the way we want it to operate. It's still not going to operate the way we want it to operate. But if I change the 1036 to 2060, now we have taken control. So that is how you will be able to know that that is the exact amount of the buffer that we need to take control of the EIP. So we go down to the answer of the answer, which is 20, as you can see from the image as well. The image showing us the exact buffer we need to use. So that's 2060. So now to answer the second to the last question, you submit the size stack space. So to submit the size stack space, this is simple. It's a simple command we will use here. Info registers EIP, we have the info registers EIP, but that's not the command we need. So we'll be using a simple command, info proc mappings command, we'll be using that to get the EIP. We'll be using the info mapping command. So in order for you to have an understanding, we can start with the info. We can start with the help info command that is going to provide us all the commands that we can use on the debugging software. So we're going to look around for what command we can use to get the stack. So we can see info proc. So this one shows the process information about any running process. So if I copy and paste it there, it's going to show me only the running processes. So those are the processes that is running currently on the system, but that's not the command that we need. So the command that we need is info proc mapping, and if I click on enter, then you see the stack. Yeah, so that, as you can see, the stack 0/22000, that's the slash, and that's the answer. That's the answer that we need for the second to the last question. Now to answer the last question, now this is where what we learned initially about the bad characters come in place. So if you remember, we identified 4 bad characters, so we'll be using the same 4 bad characters that we identified for the shell code. So it's going to just be a simple command that we're going to use. So the command that we're going to use, if we go back to the notes, we can see from down that the command that we're going to use will be, we're first going to copy the listener. So for the listener, please take note that you have to create another terminal. So you have to create another terminal. So you're going to create another terminal, which is the victim machine terminal, where you're going to be listening. So that's where you're going to be listening for the target, right? So what I'm going to do is I'm going to SSH again back into using another terminal. So I have 2 terminals that is open now. I have one that I'm going to be using the debugging tool to gain access, and I'm going to use the other one is going to be listening, right? Which is what I'm trying to do, is trying to elevate the privileges. What happens is if you don't use the terminal, if you use your own attacking machine terminal, you won't be able to gain access as a root. You only gain access as an HTTP student, right? So to be able to gain access as a root, you have to use the same terminal that you're doing. So now I'm listening on the terminal, and now to run this command, which we've already done initially, I'm going to copy it. I'm going to copy the command. I'm going to copy the command, then I'm going to go back to the terminal. I'm going to paste the command here, right? Good. So what I'm going to do now is I'm going to click scroll up to, then I'm going to go and copy. I'm going to go and copy the command. So remember, in order for you to elevate privileges, you must start with a slash. Dot slash. That dot slash means that you are running the application. As you can see cond, which means I've gained access to that, and you can see the connection has been received. So now the connection has been received. I can now try to get the answer to the last question, which is the flag.txt. So if I do cat root.flag.txt, okay, saying bin / not found. So okay, so let me try again. Let me check who am I. Okay, I'm the root. Yeah, that's good, so I can gain access to it. So it has to be for my command. So let me try my command again and see, and boom, and that's the answer. So that's the final answer to the question there. So I hope you're able to understand and learn what it means, and go through it yourself, and you'll be able to get a deeper understanding. Thank you very much for watching, and thank you, and have a wonderful rest of your day. Bye.